Okay, so let us start today's discussion. So welcome to the class. Let me know the screen is visible. Hope the screen is visible to you.
Yes, sir.
Okay, done. Thank you. Now, we were discussing about the assembler features, but from a mission independent perspective. So we have initiated 5 of them: literals, expressions, symbol defining statements, program blocks, control statements. And these things are part of our mission independent assembler features, which we will be discussing, or some of them we already discussed as well. And literals, expressions, symbol defining statements, hope we have an idea. So literals are basically, as the name says, they are part of the program where the value is literally given in the instruction itself. That's how we will be able to understand the values given to the instructions. But there might be some issue with respect to the immediate operand. That immediate operand also we have seen how different it is going to be with respect to literals. So if you look at the difference, literals are stored somewhere in the system. Their address is considered as a operand, whereas immediate addressing means the value directly is going to be part of the mission object program. So that is a basic difference. And we have also seen with respect to literals can be pooled in a given program wherever we want, so that we can try to avoid the format 4 instructions. That's what we have seen. So that's how literals are used. And we have seen LTORG as one of the assembler directive that facilitate literals. Then we have seen expressions. Expressions are 2 kinds. One may be a relative expression or an absolute expression. We have seen based on the value that is attached to the operand, we have identified if the given expression is relative or a absolute. Then we have also seen symbol defining statements, which are going to be of 2 categories. One is EQ, other one is ORG. EQ is mainly to improve the readability, and second, to assign values to the registers that we are going to use in the program, so that they can ease the burden from the programmer or maybe from the system perspective. Then ORG, where you want to assign values immediately after providing the memory for a given data. Probably we can use that. That's why we say indirectly changing the contents of a location counter in the other sense can be done through the ORG. This is what we have seen with respect to literals, expressions, and symbol defining statements. Now the important one, the program blocks, is what we are going to discuss. So as the name says, program blocks. Now let us consider a given assembly language program. We have written, say, 100-line program, let us say. So from the beginning till the end, the program is taken one after the other. The contents are considered, which are going to be data or instructions. They will be assembled in the same fashion. That is a typical usual process we see from the object program creation perspective or any assembly point of view. Now the question is, we have been talking about format 4 instructions quite in length, meaning that wherever possible, is it be okay if you can avoid format 4 instructions? Why? Because if you use format 4 instructions, that is going to invite an extra burden from the object code point of view, wherein we may have to add a modification record for each format 4 instruction that we have used. Now the question is it possible to avoid format 4 instructions always? Maybe yes, maybe no, depending upon the requirement. If the program demands to have some data which is away from the PC or base control, if that data is required in the program, then obviously we may have to go. But the question is it possible to reduce the number of format 4 instructions to the extent possible? Then probably that is what the solution we are trying to look at, or that is what the program we are going to emulate. So given that context, if possible, through this program blocks or control sections or any independent features of assembly language, can we make sure that these format 4 instructions can be reduced to the extent possible? For example, in normal sense, I may have a 10 format 4 instructions. By using some of these concepts, if I can reduce to 5 or 6, I think we have done a good job. So dependency on format 4 instructions, if we can make very minimal, may not be able to make 0, but at least if we can make minimal, probably that's what the concept we are trying to look at in improving the efficiency of the program per se. So program blocks are one such kind of category which will provide the facility so that if we want, we can keep the data and instructions very close to each other. So how this is going to reduce the format 4 instructions? So format 4 instruction, the problem is you have an instruction, but the operand, the data is somewhere very far from the current location. So thereby, data which is not close to the instruction is creating an issue, or rather is making or demanding to have a format 4 instruction. So now the one solution is it possible to keep the data and the instructions very close to each other so that the range between the difference between this data and instruction is well within the PC to start with, because that is ideal one, or within the base relative. Otherwise, it is going to be a hectic process to have a format 4. So by using program blocks, we are trying to achieve that concept. So if you look at the concept of a program blocks here, the source programs will always contain the data and instructions and subroutines or whatever it is. And these are the part of the program, and hence they will be considered for a single object program as they are. The direction and the schedule or the order in which they appear in the source program, the same order is going to be considered even for the object program, because it is a single entity. Now what we are talking about is a concept of an assembler which can allow us to have a source program, but different locations or different modules or different areas for data and instruction. In other words, we are going to keep the data and instruction close to each other so that the difference between the memory address between instruction and data is going to be reduced to the extent possible. Thereby, we are going to avoid the usage of format 4 instruction to the extent possible, because format 4 instructions require modification record, that is a burden for the assembler. So if you avoid that, probably relocation should not be a problem. So the program blocks, as the name says, they are the concept of an assembler, which is a mission independent concept, wherein this feature of program block allow or facilitate to have the data very closer to the instruction what we have. In other words, we have a flexibility to keep the data and instruction close to each other so that dependence on the format 4 instruction is going to be reduced or avoided depending upon the situation. So that is the concept of a program block. So is it clear? The concept is clear to you? Any doubts on the concept as far as the program blocks are concerned? No, sir. I have some inputs. No, sir. So program blocks are a concept of a mission independent feature of an assembler or assembly language in which we can keep the data and the instruction close to each other such that the dependence on the format 4 instruction can be reduced or avoided. So look at this typical program. This program is what you might have seen so far. This program starts at line number 5, goes up to line number 255. They're all in continuation. Each instruction from line number 5, one after the other, one after the same sequence will be considered, and you create a object program. But look at the place, maybe somewhere at line number 105. So I'm reserving 4096 bytes, which is almost 1000 in hexadecimal. If I add that, my address is going to be around 1036. Like this, if I start adding the data of this number 4096 or one more 4096, so I'm going to push the need of the data because my instruction is at 036. My data is at 1036, and what is the instruction I have? The buffer is used somewhere here. If you look at the instruction here, so buffer is used here. From this location till the data, there is almost 1000 plus type of bytes of data, which is very far from the, if you convert that into decimal, it is going to be beyond the limit of your PC, or maybe to some extent beyond the limit of your base. So we are forcing ourselves to have a data which is an instruction depending upon this particular value. So wherever that particular problem is there, we can try to avoid that. So that avoidance can be possible because we are going to keep the data and the instruction close to each other. Similarly, look at where we have used now RDREC. So RDREC is the address. Where is RDREC defined now? It is defined somewhere here, that is at 1036. So from this location, that is 0006 to 1036, it is very huge number which is beyond your 4095. So both PC and base cannot be used. So I am going to have my trouble of going to the format 4 instruction. Thereby we have seen plus J sub here because the difference is very huge beyond our limits. Similarly here, I am at 0013, my WRREC is at 105D. Again, the difference is beyond the limits of your base and PC. Thereby, we are forced to go for the format 4 instruction. So like that, wherever this difference is there, we will be having the issue. So what is the solution now? Okay, now I am at this 0006. My RDREC, instead of somewhere here, if it is kept close to this, such that the difference between these two is reduced, then probably we can say that we are going to have these program blocks. Let me look at another program. This is the program that we have taken just now, and we have revised now using our program blocks. Let us see now. Now we have seen the problem. What is the problem? The data and the instruction are a bit away from the whatever the location they are. Thereby we are forced to have the format 4 instruction. Just now we have seen in line number 35, we have used plus J sub, but look at this instruction, the plus is removed. Similarly, we had a plus J sub for WRREC. Look at this instruction. This is possible to reduce now. That means two instructions of format 4 have been removed and replaced by a normal format 3 instruction. Why this is possible? This is possible because we have used a program blocks. So how do you say we have used program blocks? So program blocks are identified using this particular assembler directive. A assembler directive by name USE is going to be considered as an identification of a program block. Similarly, I have another USC. How many you can have like this? You can have any number of USC. Let me see the other program in continuation. This is another USC. One more UC. This is another USC. And again you see USC. And again you see USC. So USC has been used quite a good number of times, which is going to be notionally inform the assembler that yes, we have used our program blocks. So this is the concept of a program block. So program block concept is nothing but, is it possible to make sure that both data and instructions are residing close to each other so that we can avoid the format 4 instruction. In the previous program, there are 4 places I think we have a format 4 instruction. Look at this program, which is the same program we have refined using program blocks. So in this first part, there is no plus JSUB or plus format 4, we have removed. The second program also we have removed majorly, only 1 we have kept. So out of 4, we have removed 3, but we have got only 1. So 75% of format for instructions have been reduced here by using the program block. So that is a good number because 75% of modification records are also reduced, which is a good improvisation in the program. So if that is the case, how program blocks are going to be defined or assembled is the next question. So first point is program blocks are necessary if the programs are very lengthy and the programs are using format for instruction, then program blocks will come handy. They will try to reduce that format for instructions by, what is the method? By keeping both instructions and data close to each other. How close they should be? They should be close enough such that the difference between the data and the instruction will not be going beyond either PC or a base relative difference. We know that range. For PC it is minus 20482 plus 2047. For base it is 0 to 4095. If you can keep within this range your data and instruction, then the need for format for instruction is absolutely zero. Thereby, we can reduce the number of format for instructions for this. Having said that, in this program, we are able to demonstrate that we have reduced from 4 to 1 the format for instruction simply by using the program blocks. So how to identify the program block is the next question. So program, see, now we have seen the previous program. If you look at the previous program, we know that this entire program is a single block. The program starts at line number 5, goes up to line number 255. This entire program is called as a one single program block. That means by default, between start and end, if there is no USC in this program, there is no USC, right? Then whatever you see between start and end is going to be considered as a one single block. Thereby, by default, this is a default block. That means whatever you see between start and end, in the absence of a USC statement, is going to be considered as a one single block, which is a default block. So far, that's what the case. Now, since we are incorporating program blocks and we can use USC at multiple places, let us see how this is going to be used. Now, before we proceed, so let us add USC to the list of assembler directives. I think in the previous class, you might have stopped at EQ org. So next, you might be adding this USC probably. You can add USC as a assembler directive. So we have added so many so far. Now you can add USC. So add USC as the assembler directive. The purpose is to create program blocks. Okay. Now let us come back. Now this program we have rewritten using program blocks now, where USC is used now. Since in the absence of USC, everything is a single block. So we start from the start now. So your program block has started. What is this program block? This is a default block, because just now we have seen in the absence of USC, whatever you see between start and end is going to be one block. That block is nothing but a default block. Now we have started and start as usual. We'll go. So assume there is no USC here, then I could have went up to END. I could have considered it as a single block. But now in this program, I have something called as a USC. So this USC is informing the assembler that, okay, you started from start, you come up to this line, that is line number 70. This is one block for you. So this is one block. So from start till you encounter a USC statement, this is called as one block. What is the name of that block? That block name is default block. Now at this point of time, I am starting a new block. What is the name of that block? That block name is C data block. I am giving some name. So it means up to this is one block. By default, there is no name for that. We call it as a default block, like your case 1, case 2 in our C++ switch case, like a default. We have a default block. But as and when you encounter a USC in the program, the previous block, program block, will stop and a new block will be starting. What is the new block here? USC C data. How long this will be in force? Until you see another USC or you reach the end of the program. Now second block has started now. The second block is, let me take another pen. The second block is this, which is going to start at line number 92 and it will go until you reach the another USC. So this complete block is a C data block. This is a new block, which is a C data block. Who is given the name? You as a programmer can give the name what you want. This is a C data block. So between line number 92 to line number 100, whatever you see, this is one block. What is the name? C data block. Then at line number 103, we are starting another block. What is that another block? That another block is nothing but, what is the name? The name of the block is CBLKS. How long it will go? It will go until you see another USC or you see end of the program. So at this point of time, it starts at 103. It is going up to 120. The name of the program is, the name of the block is CBLKS. Now, in this part of the program, what you have observed now, the same program we have rewritten using program blocks. Why we want program blocks? Because using program blocks, we can avoid the format for instructions. How do you avoid the format for instruction? Simply by keeping the data and instructions close to each other, such that the difference between the address is within the range of a program counter or a base register. If we can do so, we can avoid the format for instructions. In this process, what we are doing now, we are writing a program and in between we are bringing new program blocks, that is USC. So USC use is going to be a assembler directive which denotes the assembler that yes, now onwards I am going to create a new program block. Like that, how many program blocks you can create in a program? You can create any number of program blocks as the case may be. In the absence of USC statement, entire program is considered as a single program block, which is a default block. Otherwise, depending upon the name that we are going to give, a new name will be given to that program block. Now let us see. So from the start until you see the another USC, in this case at line number 92, we take that as a default block because there is no name for it. It is by default is a default block. Second, at line number 92, we are seeing an USC statement, which is an indication to the assembler that now onwards, I'm going to create a new program block. What is a new program block? The name of the program block is C data. Now, how long it will be in force? Until you see another USC or you reach the end of the program. So we are encountering another USC at line number 103. So between line number 92 and 100, whatever you have is going to be part of your C data. Now, the another, maybe the third program block encountered at line number 103 is having another name called CBLKS. Using that name, the new block is created. How long this will be in force? So far, it is at line number 120. Let us see the next part of the program. Yes, up to line number 120, it is in progress. At line number 123, we are encountering USC. Okay, we are encountering USC. So please be careful here. We know that we can use USC any number of times. Now this is the probably third time we are using USC in this program. First time for C data, second time for CBLKS, third time there is no name here. Please observe here. There is no name. So this USC is nothing but the default USC, meaning that the default USC has started at line number 5. It came up to line number 70. After that, default block has stopped. Now again it is resuming at line number 123. So when there is no name here, this is nothing but a default block. So default block continues now after 70 from 123. How long it will go? Until you see another USC. So you are encountering a USC at line number 183. So till this, that is from line number 123 to 180 is continuation of a previously stopped block. We have a block by name default. It stopped at 70. Now again we are resuming from line number 123. How do you say we are resuming now? Because USC we have used, but there is no name. No name means it is the default block. So let us see to get clarity. At line number 183, again we have got one more USC. If you look at this, USC, what is the name of the block now? C data. And you know that C data we had already here at line number 92. It went up to 100, stopped there. Now again C data is resuming, continuing from line number 183. How long? Till 205. So that means a block of data need not be at one go. It can be at different stretches in the given program. Only thing is logically they will be rearranged. How they get rearranged we will see shortly, but this is how we can split. That means you need not write in the single phase or single stretch a given block of program. You can divide that into multiple chunks and create the program blocks accordingly. So second program block by name C data is again resumed here and stopped. Second, one more USC we have here. Again, what is the USC here? Is a plain USC. There is no name. Since there is no name, what is the meaning now? The default block, which was stopped at line number 180 now, is resuming again at line number 208. How long? Either you see another USC or you reach the end of the program. In this case, it is at line number 245. At line number 252, again one more USC has come into picture, where that USC is belonging to C data. So C data stopped somewhere here at line number 205. Now again it resumed and stopped it here. So that's how we have got a C data being resumed again further. So like this, the given single unit of program is divided into multiple program blocks. In this case, 3 program blocks. Wherever you have seen now, you have seen either a default block, you have seen either C data block, we have seen either a CBLKS block. So these are the names that we have given to that. So this is how the single program has been identified. So we are not able to visualize the effect of this right now because we have not gone to the assembly of it. It is only source program. When you go to the assembly, probably you will see the advantage of it. But clearly in the source program, we have avoided the format for instructions. So any doubts at this point before we go how to assembly? Quickly go through that. Let me take attendance in between. Let me know if you have any doubts the concept so far. So what is a program block? Why is it required? How it is used? And how to understand the source program. If you have understood this, probably I can go to the assembly. Otherwise, if you have any doubts in this, please let me know. So meanwhile, let me complete the attendance. Asta?
Present, sir.
Now? Aishwarya?
Yes, sir.
Aishwarya?
Yes, sir.
You need to be a bit louder. Ambrish?
Yes, sir.
Anu?
Present, sir.
Arbaz? Arjun?
Present, sir.
Ashok?
Present, sir.
Benita?
Present, sir.
Bhargavi?
Present, sir.
Bhavisha?
Present, sir.
Chaitra?
Present, sir.
Chatterjee?
Present, sir.
Diksha Manjunath?
Present. Present, sir.
Deepika LG?
Present, sir.
Deepika MB?
Present, sir.
Murli Krishna? Gangubai? Guriya Kumari?
Present, sir.
Harshit?
Present, sir.
Gunjar Singh?
Present, sir.
Kavya? Kishore? Lata?
Yes, sir.
Manisha?
Present, sir.
Manjunath?
Yes, sir.
Nayana?
Present, sir.
Nilanjan? Nishant,
Present, sir.
Pavitra,
Present, sir.
Maithili,
Present, sir.
Priyanka,
Present, sir.
Pavan Kumar,
Present, sir.
Akash,
Present, sir.
Akash,
Present, sir. I'm present, sir.
Rajeshwari,
Present, sir.
Rakesh,
Present, sir.
Ramya,
Present, sir.
Rashmi,
Sir, present, sir.
Ravi Shankar,
Yes, sir.
Rizwan,
Present, sir.
Vishal,
Present, sir.
Savita,
Yes, sir.
Shruti,
Present, sir.
Sneha,
Yes, sir.
Purti,
Present, sir.
Srinidhi,
Present, sir.
Srinivas,
Present, sir.
Sunil, Vaishnavi,
Present, sir.
Vinny.
Present, sir.
Okay.
Sir, Kavya present, sir.
Sir, Murli Krishna.
Okay. Fine.
Sir, Murli
Any
Krishna also
doubts?
present.
Fine. If you have no doubts, let me resume with the discussion. So that is how the program has been identified now. So this program of original program has been converted into program blocks. We know how to use USC. I've just listed for your understanding perspective. That is, but using USC, whatever you have seen now, I've just written here for your just understanding. Now, once that program is written, how the assembly is going to take care? Because normally, if you look at the assembly of the program, pass 1, location counter gets initialized, keeps on adding 3, 4, 2, whatever it is. At the end, it stops. That was one process. Now, when you have a 3, 4, 5, 6, you can have any number of program blocks, and the one program block stops at one place and resumes at some other place. If that is the case, how many location counters we require? Is one location counter sufficient? Definitely no. So we require each program block to be assigned with a separate location counter. Meaning that if we have 3 program blocks in our program, what we have seen, we have a default block, C data block, C blocks block. There are 3 program blocks. So how many location counters are required? 3 separate location counters need to be created. Suppose I have another program where I have a 5 program blocks, then I need to create a 5 location counter. So your system should be capable of handling program blocks by adding individual or independent location counters, so that when you have this program block concept, each location counter will be dedicated for the program block concerned, and that will resume further as and when the program block continues in the due course of the program. So assembly means how we are going to assemble the program involving the program blocks. The first case is for every program block, an independent location counter need to be initialized. So that is the first one. Once that is done, as we go from one program block to another program block, the location counter is newly created, and when the already existing program block resumes, like we have seen default block, C data block coming at more than one place, the corresponding location counter will be updated. That's how the pass 1 is going to be, and accordingly all the labels what we have in the pass 1 will be stored into the symbol table. So first concept of assembly is having an independent or individual location counter, so that the location counter resumes the work as and when the blocks are going to be repeated or resumed. So in our program, we have given 3 names. One is default, other one is C data, third one is C blocks. So how the assembly is going to happen is what the question now. So let me see if they have a program. Yes. So this is the program what I have taken just now. So the difference between the other program and this is we have a mission address in addition to that. So mission address was not there. Now we have got a mission address. Now we know that from line number 5 till line number 70, this is completely a default program block. That is up to this is a default. I'll just write D. Now there is a USC here. Because of this USC, whose name is C data has block has started up to this. So between these two, we have a C data. We have another block by name CBLKS. It started here. It is there up to this part. This is what we have seen now so far. Now you look at the location counter. Location counter is initialized with 00 for this default block. It comes up to this line 0024. Suppose if it is not a program block, this would have become a 0027, 0030 like that. But see now the new 00 has come, meaning that since it is a new block, the location counter is reinitialized, meaning that a new location counter is taken. You can see that here. Similarly, when you are here at new block, new program block by name CBLKS, again it is 0000, meaning that a new location counter is got initialized. Okay, that's what we have to see. Now second, so in continuation we have another USC where default USC. So default what we have will resume here. So what was the default we have seen now? Let us see whether resuming or not. We stopped at what? 0024 plus 3. Next should be 0027. You can observe this here. It was 0024 earlier. Now it has become 0027. Why? Because this is not a new block. This is an already existing block. It is only continuation. So where it was stopped earlier, 0024, and that instruction ends at 0027. So 0027 will become the address of this instruction. How long you will go like this? Until you see another USC statement. You are seeing USC here. So this is USC C data. So let us go back to C data because C data is not new. It is already existing. So C data was 00 and stopped at 3. 3 plus 3. RESW1 means 3. 3 plus 3, 6. Let us see whether C data is resuming at 6 or not. See, C data is resuming at 6. So this is a continuation of an already existing block. Like this, how long it will go? Until you see another USC. You are seeing another USC for default block. So where is the default block earlier stopped? Stopped at 004A. Now we are taking another, that is R sub, some instruction. So 4A, B, C, D. We are starting at 004D. So 4A was there earlier. Now it is continuing. Like that, location counter of one program block will be reserved for each program block and resumes as and when, or continues as and when the program blocks is repeated in the program. So like that, we keep doing. Again, we have USC here, C data. So C data stopped at 0006. So probably it will start at 007 because we have used only 1 byte. It's only 1 byte. So 006 plus 1, 007. So like that, each program block will be assigned a separate location counter that gets resumed. If that is the case now, let us know what is the starting point of a first block, that is the default block. Default block starts at 00, goes up to 24, again continues from 27, goes up to 4A, again starts at 4D and comes up to 0063. That is the starting address. 63 plus 3, 63, 64, 65. So 0002, 0065. Is it clear now? Able to understand? The first default block starts at 00 and comes up to 0063. That is the starting address. Where is it ending now? 63, 64, 65. So 0002, 0065. Total how many? 66 bytes. So that's what we have listed in the diagram here. Look at this. We started at 00. Went up to 0065. What is the total length? 66. Okay. Now C data. So C data, because this is only from the pass 1. When you go to pass 2, it should be projected as a single program. So when you project as a single program, There is no program block concept at that time. Everything is clubbed together. When you want to club together, the same order will take. So first default block has come. After that, C data block has come. So where is the C data block? It is ending at 0007 and 0007, 008, 9A. So 10 we have added. So let us see how much we have added now. So 0006 up to 000B. So like that, you continue from the default, goes to the next immediate block, like that you keep on adding when you are in the pass 2. Only during pass 1, location counters are independent. The programs are going to be given independent location counters. Accordingly, the address is given, and once they know that where are those pending blocks are there, where they are going to resume, they will be put together. That means at the end of pass 2, entire program block is projected as a single block only. That's what we started today, the discussion. Normally, the programs are projected as a single block. Even now, there is no change. Even in the concept of a program block, when it comes to the object program, the program is pretty same. But internally, that's why we have used the word, the logical arrangement. Look at this. Program blocks are nothing but the logically rearrange. The logical rearrangement is what we have seen now. That means default block, C data block, C BLKS block, they get logically rearranged. How? Look at this diagram. So this is what is happening. So we had earlier, if you remember, default block, then C data came, then C blocks came, then default came, then C data came, then default came, then C. This is the original program. So what happened at the end? See, all defaults are kept at one place, all C data are kept at one place, or C blocks are kept at one place. So from memory point of view, you don't see any change. Similarly, depending upon the size, default 1, 2, 3, they will be kept at for object program. So from memory and object program point of view, they will be considered as a single block of data only. Only for the source program, for internal rearrangement, they will be pushed so that both data and instructions are going to be reaching together or commonly. That is the idea. But outside, object program is same. All default are pushed together. All C data are kept at one place, or C BLKS are kept at one. Like that, you can have any program block and all of them will be togetherly stored when it comes to memory. But internally, in the source program, they will be arranged such that the data and instruction are close to each other. Thereby, we can avoid the or reduce the format for instruction. So more clear picture. Whatever I have written in black and white, that's what available. This you can see that now with address. Okay, these are the program blocks are going to be considered. So program blocks are having a initially independent location counter in pass 1. Once pass 1 is over, they will be visualized as a single entity only. At the end, this is object program. I don't think you'll see any difference here. This program is pretty same as the previous program. Absolutely, you will see no change because there is no additional. But you can see one change here. The modification records have been reduced. That's what we want. By using program blocks, are we going to avoid or reduce the format for instructions? Yes, we have done that typically here. That's what we mean by the advantage of a format for instruction. So this is what the concept of a program blocks. So any doubts here? What is the concept here now? Program blocks. What are the program blocks? They are the mission independent assembler features. Why do we need them? We need them to avoid or reduce the number of format for instructions wherever possible. Is program block is going to help in that way? Yes. How? By keeping the data and instruction close to each other in the source program, we can do that. How it is being done? It is being done using the USC assembler directive. So by using USC, any number of times in the program, we can divide the given source program logically into various blocks. And each such block is going to be a program block. So by default, whatever you see between start and end is going to be considered as a single block, which is called as a default block. Otherwise, whatever you see between a start and the encounter of another USC is going to be called as a default block, as we have seen in the program. So depending upon how many number of blocks we have, so many number of USC statements can be there, and the same block can be repeated in the other side of the program or in between the program, so that when it logically gets rearranged, all those similar kind of program blocks will be put together as you've seen in the diagram. So they will be put, all defaults will come together, all C data will come together, all CBLKS comes together. Only in the pass one, each program block is assigned a separate location counter. Later in pass 2 and the object program, every program is united. It will be projected as a single object program. So what is the advantage then? The advantage is like this. We can reduce the number of format for programs, and program readability is easy. Then what is the overhead? Overhead is having more number of location counters and making combination of these two at the end of the pass one is a what you call as a overhead, because every advantage will have a disadvantage also. The advantage here is we want to reduce the number of format 4 instructions, thereby modification records can be reduced, and hence relocation problem can be reduced. What is the disadvantage now? To facilitate that, we need to have a more space for the location counters and some control to club all these at the end of the program. This is how it is going to be done. So this is the concept of a program block. So this is what the today's discussion. If you have any doubts, please let me know. Otherwise, I am done with the discussion for the today's class about the